everyone, thank you so much for clicking onto the video. Now we're going to look at some harder questions. So for the first question, write an equation for the process that has an enthalpy change equal to the electron affinity of chlorine. And so the definition of electron affinity is the enthalpy change when you add an electron to 1 mole of gaseous chlorine atoms to form 1 mole of gaseous 1- chlorine ions. And so what we're doing is we start off with 1 mole of chlorine gas, and then we add 1 electron and we form 1 mole of Cl- gas ions. And then for B, in terms of electrostatic forces, suggest why the electron affinity of fluorine has a negative value. Well, because we're adding an electron, there's a force felt between the positive nucleus and the electron. And so energy is released because there's a kind of bond, an electrostatic force forming between them. And so energy is released. So it's an exothermic reaction. So the enthalpy change will be negative. So there's a force between positive nucleus and negative electron, and this means that energy is released. And then for C, complete the Born-Haber cycle for silver fluoride by adding the missing species on the dotted lines and calculating the bond enthalpy of the fluorine-fluorine bond. Okay, so at the bottom we always start with the enthalpy of formation. So we're trying to form the silver fluoride, and so the other thing we need is fluorine. And fluorine exists as a diatomic molecule, so in twos, and it's also a gas. And so to balance it, that means we need half of these fluorines. And then the next thing that happens is that you see that this silver has now turned into gas. So because we represent one change using one level, that means that the fluorine hasn't changed. So we've still got half of that fluorine gas. And then the next thing that happens is that they've taken the first ionization energy of silver. So again, the fluorine is unchanged. And then to get to the top, they haven't done anything. So that means that we need to change this fluorine. And if you have a look at the other side of the cycle, they have F-, the gas. And so this gives us a clue as to what we need for this top level. And we actually just need fluorine as an atom, as a gaseous atom by itself. Actually, for the level that we've just done, we need an electron because they've taken an electron away from the silver to get the first ionization energy. And then for the top level, we're going to form 1 mole of fluorine, and we're still going to have that electron because we haven't done anything with it yet. And then this should work because the next thing that happens is that they take the electron affinity for fluorine, which means they've added that electron to the fluorine to form F- gas. So all of this works. And now it tells us to calculate the bond enthalpy. So I'm going to write all the numbers in a different color. So the first one we have is this enthalpy of formation for the silver fluoride. So that's minus 203. And then the next thing that happens is that we atomize the silver. And so we have plus 298. And then the next step is they've taken the first ionization energy for silver. So that's going to be plus 732. And then for this step, we have to be really careful because we need to remember our definitions. They have broken that bond. So we're trying to find this bond enthalpy, which means that we're breaking 1 mole of these FF covalent bonds. And because we're only breaking half of them, that means we need half of this value. And so what we have is, because it's unknown, and what we have is that because it's unknown, we call it X, but we actually have half of X because we're only breaking half a mole of these FF covalent bonds. And then the next thing that happens is this electron affinity for fluorine, and that is minus 348. And then the last thing that happens is that we've got the enthalpy of lattice dissociation for silver fluoride. So that means we're breaking the solid ionic compound into its separate constituent ions in the gas phase. And so that's why the arrow is going up. And this is plus 955 because it's an endothermic reaction. And so now we can start to form the equation for trying to get the unknown bond enthalpy. And so we use Hess's law and we think, where should I start and where should I finish? So there are a few ways that you can do this. Some people like to swap the signs around so that they can do the same thing as we've done before, but just swap the 203 and the 955 into plus 203 and minus 955. So that works. Or you can choose to start and finish somewhere else. So if I choose to start here, but I finish here, then I can keep all the signs as they are, but it will still work. So we have an equation that looks like this. We have 298 plus 732 plus half x minus 348, and that is equal to minus 203 plus 955. And rearranging that gives us that half x equals 79. And so this gives us that x is equal to plus 158 kilojoules per mole. And it should be a positive number because we're breaking covalent bonds, so energy is needed for that. So it's endothermic reaction. Before I go on to question 2, feel free to try it out for yourself first. So a theoretical value for the enthalpy of lattice dissociation can be calculated using a perfect ionic model. And the theoretical enthalpy of lattice dissociation for silver fluoride is plus 870 kilojoules per mole. Explain why this theoretical value is different from the experimental value that can be calculated using a Born-Haber cycle. Well, the key thing to remember here is that when they calculate this theoretical value, they assume that perfect ionic model. And this means that they assume that the ions are perfectly spherical. And this isn't the case because ionic compounds actually have some covalent character depending on the compound. And so the answer is that there is some covalent character present. And therefore we cannot assume the perfect ionic model as it will be inaccurate because that's assuming that all the ions are perfectly spherical, whereas if they have some covalent character, then we've got some polarization, so some distortion of the ions. And then for B, the theoretical enthalpy of lattice dissociation for silver chloride is plus 770 kilojoules per mole. Explain why this value is less than the value for silver fluoride. Well, if you think back to polarization, for something to be really, really good at polarizing, the ion needs to be quite small. And so fluorine and chlorine, they're both in group 7. However, fluorine is one above. So that means that the fluoride ion is much smaller than the chloride ion because it's got one less outer shell. And so that means that it's attracted to the silver plus ion more closely than the silver chloride ion. And so that's why the enthalpy of lattice dissociation is bigger because the ionic bonding is stronger. So the answer is that fluoride ions are smaller than chloride ions. And that means that we have stronger ionic bonding to that silver plus ion. And so the lattice enthalpy of dissociation for this silver fluoride is a lot bigger.